Hello and welcome to Mining Big Data. Sorry I couldn't make it on Friday. I had quite a severe back injury and I couldn't stand up, so I didn't come to work. And I couldn't sit down either, so I was just lying on the floor for basically the better part of a day. But I have recovered a little bit and I've been to a physio, so hopefully no problems in the near future. Sorry for the inconvenience. So today we're going to be recording from. Today will be pre-record. On Friday is a public holiday. So again, we're going to run into the same problem. I think I'll probably have that lecture up by Tuesday next week instead of by Friday, because Friday is a public holiday, as I said. I might do it over the long weekend, I'm not sure. But because you guys can't come, it will be another pre-record. If you have any questions, you can always post them to the discussion forum, or if they're very urgent, you can email me. Of course, I'm not available on weekends, as some of you will have discovered from the late replies that you received this morning to your emails about the assignment, which was due. I hope you all did really well, and I hope my short video on it was helpful in framing what you were trying to do. Okay, so today we're going to be talking about deep learning. Oh, sorry, and assignment 2 will be up shortly too. Deep learning. Okay, so let's talk about what we're talking about today. We're going to be talking about deep learning in general, parameters and hyperparameters, some stuff on autoencoders, generative adversarial networks, recursive neural networks, long-term, short-term memory units, and GRUs. So it's basically a whole bunch of different what we call it, deep learning technologies or architectures that we can use that allow us to perform particular kinds of tasks. And yeah, just some general information about them. I don't know. Some of this will be revision. A lot of it may be revision for some of you, but I thought I'd just give my take on it in a sort of a detailed way to see whether I could, I don't know, provide some insight into how these things work. So let's have a look. Neural networks are otherwise known as how computer scientists don't understand brains at all. It is true. Okay, so just some revision questions. Let's see. How many parameters are shown in this fully connected neural network? This was designed for Friday, so give me a break. We had a bunch of choices for answers, right? 13, 46, 36, 49. All right, so some of the easy answers might be, it's the number of nodes. The answer to that is no. So it's definitely not A. There are 13 nodes, but it's definitely not A. We've also got 36 and 46. Okay, well, let's do some math. There are 3 here and 4 there. So that means there's 12 connections here, 16 connections there, and 8 connections there. So what's that? 12 plus 16 is 28, plus 8 is 36. So are there 36 different parameters here? No. Because we've got to have weights for each of these things, right? Each of these has a weight, but they also have a bias associated with them, right? So it's going to be a little bit more complicated than that. So how many are we going to have in total? Well, these ones won't have biases associated with them, right? Because they're just inputs, but these 10 will, right? So 49 would be if they all had biases, right? Each one had a bias, each node had a bias. That would give you 49, but we don't have biases with these first 3. So the answer is going to be these 12, one weight for each of these 12, one weight for each of these 16, one weight for each of these 8, which adds up to our total of 36, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 biases. So 46, the answer is going to be B. The next question is, what are the main components of a CNN? Well, that's easy. Convolutions and max pooling, right? Those are the 2 components. Some people have fully connected, but that's nonsense because YOLO doesn't have any fully connected. You don't need fully connected layers. You can implement fully connected layers as convolutional layers or bottleneck layers. There's a whole bunch of things. Often people will say that there's a fully connected layer at the end, but it doesn't need to be. And how many parameters should a neural network have? The answer is always more. No, as many as it needs to minimally represent the problem. So, like basically the answer to that question is, how many parameters should it have? How many layers should it have? What cost function should you use? What activation function should you use? All of these really depend on the problem, right? So, the number of parameters that an NN should have, we don't actually know, right? So like, we don't really know how complicated image recognition actually is. right? We've built these systems that do image recognition, right? That can recognize a cat versus a dog, but we don't actually really know how complicated the task of recognizing animals is. We don't really have a good representation of that. It's not like we can solve it. Like, it's not like, I don't know, what's a simpler example? You know, anything where we can do some clustering analysis, or we can draw lines or linear regression. Those are all problems that we could make some pretty good statements about what the complexity is. When we're trying to linearly regress one set of data with another set of data, what we're saying is there's an X to Y relationship. X is some multiple of Y. Y is some multiple plus of X, maybe plus an offset, right? And so that's what we're saying the complexity of that data is. We do not actually know at a fundamental level how complex image processing and image recognition is. We don't know how complicated language processing is, right? We don't know what the natural complexity of these tasks are. We sort of estimate them and approximate them using neural networks, but we don't actually understand the underlying problem. If we did, we wouldn't need to use the black box neural network approach. We would just solve the problem manually. But the problems are obviously very, very complicated, very nuanced. And so what we're doing is we're using approximations instead. So the answer to all of these questions is what one works best for the application that I'm looking at. Like, does adding momentum to my cost function, or like my optimizer for my cost function, does that make sense? Does adding an extra layer make sense? Should I have skip layers? Should I have bottleneck layers? Should I have ... layers? The answer is, does it work or not? But the main two things that we're trying to work on, right, like all of these questions are trying to answer is, am I overfitting my data? Am I underfitting my data? Am I perfectly fitting my data? Because I want the black line. I want the black line. Sometimes I'll get the green line. Sometimes I'll get the red line. I don't want the red line. I want the black line. So all of these questions sort of come down to those kinds of answers. Okay, so that's the basic revision, right? So these are the things that we should know about neural networks, kind of like what a neural network is, what all the words that I used mean. So if you didn't understand the first part of this lecture, you need to go and do some more revision. Okay, so let's talk CNNs. What are these pictures of? Stop for a moment, ask yourself, what do I think this is a picture of? And the answer is, you have no idea, right? It's actually a picture of what are these pictures of, right? So these pictures we don't know, these pictures we do. Okay, so I'm guessing you can guess that this is a picture of a dog, right? So these are also pictures of dogs, right? But the difference is that the way that I made this picture of a dog is I took this original picture of this dog, right? And I swapped every row on the right with every other row randomly, and I swapped every column with every other column randomly, right? And we can see here that, yeah, maybe we could imagine there was a dog in this image, maybe if we turned our head sideways, although I'm pretty sure that if I just gave you a random one of these, you wouldn't be able to tell. And then likewise, with this one, I just changed every pixel with another random pixel, right? So this is all the information of the dog, every pixel, just in a different location, right? And we can see here that these two are completely unintelligible. Okay, so what did I do here? Well, in this case, I just ran a filter over it to get rid of all the color texture, right? So basically, this is just all of the edges of the image, right? We can see reasonably clearly that there's a dog, right? So what is that telling us? That is telling us that there's a lot of information there, right? That the edges are important, right? Because if I can still recognize the dog after having removed everything but the edges, I know that edges contain information. Likewise here, what I've done here is I basically took every set of 4 pixels and I scrambled them. And then I took every set of, every group of 4 pixels in 4 pixel groups, and then scrambled those. And then I took those megapixels, which are 16 pixels big, and I took them with their next 4 neighbors and I scrambled those. And I just scrambled up in a sort of fractal way from all the way to the bottom up a number of steps, right? And what we can see here is that even though we don't really know that what this is, when I tell you that it's a dog, it's quite believable that it is a dog, right? And if you blur your eyes and squint a bit, right, you could sort of imagine that this is kind of an abstract art version of a dog. So we can see that there's some information that's been preserved here, right? Likewise, we can see a lot of information has been preserved here, but some information has been preserved here despite all of that noise that I've shuffled in, right? As opposed to here, where all of the information seems to have been completely scrambled out, right? I have no idea that either of these are dogs. I do have some sense that this could be a dog, right? I can see something that resembles eyes here. I can see something that resembles a nose there. I can see some general features. And so if you told me that this was that, I could relatively easily believe you that that is true, right? Okay, so this is what I did, right? So this is the description. And we can see here, what is the assumption that we're making, right? Why am I telling you all of this stuff, right? So this is a two-dimensional convolution. This one is just using this filter here. So you multiply this filter by the whole image and basically pick out all the edges. What is the point that I'm trying to tell you? Okay, so when we get later, where's later in the thing? Later, what we're going to see is we're going to see a whole bunch of diagrams that look like this little thing here, the blue boxes, right? Each of the 3 blue boxes. The smartness that underpins a convolutional neural network has everything to do with these images here. What it's saying is that that's where all the information in the image is, right? At the low level, it's the edges. At the high level, it's this sort of fractal size hierarchy of where the information is. And that has defined why we build convolutional neural networks the way that we build them, right? So when we get down to like all the max pooling and all that kind of stuff, this stuff will make a lot more sense. Okay, so this is a convolution. What are we doing? The way that a convolution works is we take the image and we imagine the image is made out of some kind of data, right? So in the case of the dog, it's going to be numbers between 0 and 255. And what we do is we take our convolutional filter, we cross multiply each of these numbers by its corresponding color, right, to get a product, right? So this is -1 and 1. You can see -1 and 1. This is 0 and 3, 0 and 3, 1 and 5, 1 and 5, -1 and 2, -1 and 2. And we do all of these, and then we add them all together, and we chuck them in the new image, right? And believe it or not, there's a bunch of different convolutions that do a bunch of different things. So this is a smoothing one, right? So basically, we take every pixel and replace it by the average of the 9 pixels around it. And then we end up with this kind of blurrier image. And then this one is a sharpening filter. It's doing the opposite. It's taking every pixel, multiplying its result by 9, and then subtracting from it each of the points around it. And what you can see here is that all of the little differences are much more pronounced, right? So you can see each little hair very, very well, right? But if you look at the image as a whole, you can see that it's a little bit less the lights and the darks. You can see all these little differences, but the bigger differences over bigger spaces are a little less obvious, right? Because some of that will have been taken out and dominated by the small differences, right? There's less texture at higher frequencies. And in this one, this is an edge detector. Basically, it's picked out all of the vertical edges, and that's why we've got the picture of the dog. So it's giving you an idea of what can a convolution do. A convolution can filter out certain information, and it can filter out, like this is filtering out all of the low-level information. This one is filtering out everything except the edges, right? This one is filtering out some of the texture information, like the low-frequency texture information. So nice and neat, right? Okay, so what are we going to do? What are we going to do next, right? Okay, so why wouldn't we, if we were trying to do something, like what we're going to do is we're going to train a neural network. And what the neural network is going to do is it's going to learn a whole bunch of these filters, right? And we're going to train it so it learns lots and lots of different filters instead. Each filter it learns is going to allow it to see the image in a different way. And then we're going to take each of these filters and we're going to do it again, and we're going to learn lots and lots and lots of them. And eventually, believe it or not, if you do enough filters on an image and then you downsample it and then you filter it again and you downsample it, eventually you end up with a classifier, right? Like at the end, you're going to get a pixel, and that pixel, you can actually make it so that you get like one pixel, one value that tells you how dog-like the image is. And if it's 0, it's not a dog. And if it's 1, it is a dog. As strange as that sounds, but that's basically what's going on with these convolutional neural networks. We're going to multiply an image by a lot of different convolutions, right? We're going to train these, right? So it's going to learn all different weird numbers in between. Then we're going to downsample the image, and then we're going to do it again. And then we're going to downsample the image and then do it again, and downsample the image and do it again. Okay. Just as a quick definition, we also have padding, right? So one of the issues with padding is you can see that, like for this example here, the red is on the edge of the image, and the final result goes in the question mark. But what if I wanted to calculate this one on the edge? I don't have the right numbers here. I would need numbers over here that are outside my image. And we've got 2 choices. Basically, either you can make it so that every time you do a convolution, the image gets smaller. So it basically means you just don't do this edge region, and the result will just be this smaller region here. And the other option is that we just fill it in with zeros or something like zeros, or the average of something, fill it in with some kind of information. That's if we don't want our image to become smaller over time. So that's padding. So the next big step, right? So we've done convolutions. The next big step is pooling, right? So if we do use padding, it kind of implies that the image is never going to get any smaller, right? So we're going to start with a big picture of a dog, and we're going to convolve it, and then we're going to end up with another picture of a dog, and then we're going to convolve it, and then we're going to end up with another picture of a dog, and we're going to convolve it. So what I'd like to say here, right, is that we've got a couple of ways that we could conceive of the problem. One is that what we could say is, here is our matrix, and we want to like label dog wherever there is dog. So we can be like, this is all dog. And this would be an example of segmentation, where basically you're trying to turn the image into regions where there is an object of a class and regions where they are not an object of a class. So in this case, this would be where all the dogs are. But we also want to be able to deal with this case, right, where basically what we're saying is that these are both pictures of dogs. Now, clearly, this image and this image have literally no information in common. Like, obviously, one's translated, so there is like a correlation between them. But no pixel of this image is the same as a pixel from that image, right? There's nothing in between them, right? Like, all the information in this image is in this subset. All the information in this image is in this subset. But we want to classify them both as dogs. So at the end of the day, if you're doing like binary classification or a class-like classification, you're going to end up with single values. You're just like dog, not dog, dog, not dog, right? So we need to make the images smaller, right? Because eventually we start with a big image. The image might be 1,000 by 1,000 pixels. In the end, we want one by one, a 1 by 1 value, or maybe 2 1 by 1 values, right? So we've got to like downsample somehow. So in convolutional neural networks, there's two basic ideas. One is max pooling, right? And that's where basically you take a square and you take the largest value in that square. So you can see the 14 is the biggest of the 14, 9, 7, and 2. The 9 is the biggest of 3, 1, 9, and 4. And 91 is the biggest of 41, 91, 15, and 19. You get the rest. It's a winner takes all approach. And basically it just means that like if something's giving you a strong response, you maintain that strong response. You don't like blur it out or average it with things around it. And it's good for objects that have really sharp features, right? And that kind of makes sense. So you're looking like for small sharp features that you want to propagate up through your tree. You don't want them to get blurred out by other features in your image, right? The other kind is average pooling, and average pooling is you just take those same squares and you find the mean of them, right? So you can see here that these squares will become a mean of 8, and these squares become a mean of 4.25, and these ones become 41.5 and 28.25 respectively, right? And when you do this, basically your image will become 4 times smaller. When I say 4 times, I mean twice and twice, so 4 times, right? And so each time you do a max pooling or an average pooling, your image is going to become progressively smaller and smaller, and eventually you'll run out of image and it'll be 1 square big. So if we look at the whole structure together, right, the way it's all going to work of our convolutional neural network, we have our convolutions, right? We showed what convolutions are, and these involve like a convolution with an activation function. It can involve multiple layers of convolutions, and then eventually a pooling, right? And the way that we represent that normally is these blocks, right? So we'll have like a big block. So this is a big image. It's only got a few channels, right? So it might be red, green, and blue. And then we do some convolutions on it. And then eventually we're going to do a down sample. So we're going to do a pooling operation, and it will end up looking like this, where it'll be a bit fatter and smaller. And then likewise, we do it again. And then eventually the convention is what you do at the end is you do a fully connected layer. And each one of these represents like a class weighting. So what you're doing is you're training in saying this should be 1 and these all should be 0. And then what we do is we look at this thing, we feed a new image into it, and we go, oh, which one of these? Oh, I think it's probably this one, whatever that is. So it's probably a dog, right? Whereas this might be a lizard and that might be a bird, right? And that's the basic structure of the CNN, right? Often they'll have multiple versions of this, right? So like maybe just because I'm being a bit silly, maybe we can make this a little bit better. Sometimes it'll look like this, right? You'll have multiple convolutions at the same resolution, but the second one will have more features. Yeah. So let's see if we can do it that way. Then I didn't have it like that originally because I wanted it to be kind of clean, but I think I like this better. So we'll bring this to front, and then we'll bring this to the front, and then it will all look nice and good, right? So you can see here, I'll do some convolutions on it. And that will transform this one into that one, right? I'll end up with 3 channels. It might become, 16 or 32 or some division by 2, because they're always the division by 2. And then we downsample, and then we might have another one of these blocks that's the same size here, or we could have like lots of layers like that, and then we'll downsample, and then we'll have lots of these blocks in a row, and then eventually we'll have a fully connected layer. And there's a whole bunch of other things we could do, like skip layers, where you do direct connections from early blocks to late blocks. Sometimes you have like a bottleneck layer. Sometimes you'll have all kinds of layers. And a lot of the cleverness comes about the variety, the number, how do you stop diminishing gradients, all those kinds of things. Okay. So what differs between these? You know, like the question could be like, how big are your convolutions? They're usually 3 by 3. They started off being 5 by 5. The original, a lot of the early ones were 5 by 5, but 3 by 3 has been chosen as the magic number because computers do them well, and it seems to work really well. Sometimes you do 1 by 1. 1 by 1 layers are normally used as a way of like minimizing the amount of information. So you can imagine that you've got like a big number of parameters, you bottleneck it through a small number of parameters, and then go to a big again. The bottleneck basically makes the system more efficient. Everything has to go through a small pipe. Like it reduces the dimensionality in the space, and it reduces the likelihood of overfitting. But questions will be like, how many layers? More is usually better. How many filters in each layer? It's normally less, more. Right, so like it's very common for this to start with 3 and then go to 32, 64, 128. Do you max pull or average pull? Depends on the application. Which activation? Leaky ReLU or a sigmoid or a 10H? Are they fully connected layers? Do you even use them, or do you just use convolutions? And then other features like skip layers, bottleneck layers, dilation, padding, all those kinds of things you can fiddle around the edges with. Batch normalization is another one you can fiddle around the edges with. All right, so that's convolutional neural networks, right? So basically, like if you're a data miner, you're probably not designing your own convolutional neural network. You're just training some data and seeing whether you can build an image recognizing system. All right, so let's talk briefly about autoencoders. Now, this wasn't in last semester's version of the course, but I thought to understand GANs, understanding an autoencoder is probably a good idea. So very, very briefly, the idea behind an autoencoder is it's like a CNN, except instead of coming down to a single point where you're saying, is it a dog or not? What you're trying to do is you take the dog, you compact it down into some lower order representation, and then you build it back up again to try and recreate the dog, right? So it's basically trying to turn a dog into a dog. You might sit there going, why would you even bother? And it's a good question. And the idea is here is that like basically that this middle block should be a higher order representation. Did I say lower last time? Like it should be like more abstract, have less actual features. So every picture of a dog you can imagine could be in this giant image. This block here needs to be smaller. So it's kind of like a form of compression, make things smaller. And so the idea is that this lower order representation basically encapsulates what it means to be a dog, and everything else is noise. And by noise, I mean like if you add a dog and noise, you'll get a different dog, but it will always be a dog at the end, right? Or the dog-like thing at the end. And you can just fiddle with these numbers in here and put in whatever numbers you want. And then eventually you'll get pictures of dogs. And this is how you can sort of generically create stuff, at least theoretically. So we're turning an image to a number and then turning it back into a dog, right? And so, yeah, they have to all dogs have to conform to this like nominal idea of dog. Like, so not like we can't do it like this, right? We couldn't go all the way down to the word dog and then go back up again. Like, is they, hey, network, can you please make me dogs? That would be kind of challenging, right? Like, isn't like, how would I train this network to just create dogs out of the word dog? Wouldn't make any sense. Although we'll see in the next section, we can kind of do this. So I'm just going to pause because I need to drink because I'm like, my throat is killing me. And we're back. So that's the idea of an autoencoder. They're used for all kinds of things. Denoising is a good application. They're not used for actual compression because, you know, like there are better compression algorithms that are theoretically better. But you can use it for denoising. So here's an example from a paper where they took all these digits and they basically used the autoencoder architecture to reconstruct the digits to try and guess what they look like. Yeah. Makes sense. All seems pretty reasonable to me. It's basically trying to say that these are all pictures of digits, and that like if you you compress them and you make it think it's a 3, it's going to redraw it as a 3 that's very similar to the original 3. Kind of cute. So we have this idea of information compression and then information decompression. And you might be sitting there at this point in the lecture going, Bernard's full of nonsense. That doesn't make any sense, right? Because like, how are you doing this decompression, right? Like if this is compression, right? And this is going from lots of information to less information, what are you losing here, right? So the idea is you must be losing the noise, right? So when you're coming back up, it means you have to be inserting that noise back in, yeah? Because like max pull, if you think about max pull, like how do you reverse max pull? Yeah, like I'm taking the largest of these numbers and putting it here. If I want to unmax pull, it means I can just put anything I want there, right? As long as it's less than 14, right? So you can imagine that that's just made up. So there's noise. But yeah, that's basically the idea. We're going to do some information compression and then some decompression. All right. And this will prep us so that we can understand what generative adversarial networks are. Also known as automating an auditor. Okay, so what if instead of trying to recognize images and say which image was which is what a normal convolutional neural network does, right? I decide that I wanted to make images from nothing which conform to a particular type. Yeah. Oh, it didn't work. So the idea here is, where are we? Come on, work for me. Oh no, this is the cunning plan, right? So here's my cunning plan, right? So I'm going to take this and I'm going to flip it around, right? And I'm going to say, I want a dog. And then I'm going to end up with the crazy weird dog, right? Like, so instead of this, we're sort of flipping it and we're trying to do it the other way. Okay. So we know from the autoencoder stuff, compression plus noise is equal to an image. So if I have a compressed version and I add some noise at each stage, I should end up with an original image that looks like a dog, right? That's the dream, So to give you an idea of like an analogy of what I mean when I say compression plus noise, imagine that I have these data points and I fit the circle to the data points and I say, hey, look, it's a circle, right? And then I go, here is a circle. And then I go, I'm going to populate the data points and I'd give you these data points and I give you the same data points every time, wouldn't I? Because it's just a circle, right? This doesn't look real. Yeah, this doesn't look like real data because it's too clean. This looks like real data. This does not. And so what I would do is I'd add in a little bit of noise and then this would begin to look a little bit more like real data. Yeah, makes sense. Okay, so let's have a look. This is our generative adversarial network. So we've got two components. We have a generator and we have a discriminator. And the idea here is we take some random noise, we chuck it into our generator, which will turn it into a fake image. Then we have some real images, and then the red box, its job is to take this set of objects and this set of objects, and as a binary classification, say that some of them are real and some of them are fake. And this one will be judged by how well it selects training set ones as real and how much it selects fake images as fake. Yay, simple enough. So the generator, like as I said before, the idea is we take the random noise, we build up, we go all the way through, and eventually we end up with a fake image. So we're doing some anti-max pool operations, we're doing some anti-convolutional filter kinds of operations, which end up just being like convolutions. And we sequentially add noise that goes up and ends up with our fake image, right? And the discriminator is the idea here is that what it's doing is it's taking a real image and a fake image, and it's trying to turn out which one is real, which one's fake. This is a photo of me, and this is a photo from a website called This Person Does Not Exist, right? And this just generates lots and lots of fake photos, which is kind of cute. So the idea is how would we get this to work? Well, we want to train a good discriminator, i.e. a basic classifier. So what we do is we get some real images and some fake images, or we mostly just train it on like real images. And then we basically train that one until it's good at detecting real images. But we also want to train a good generator to try and trick it, right? So this thing is going to create lots of random images. So how does this work? Okay. So what is the discriminator learning, right? So what the discriminator is learning from a mathematical point of view is that the probability of y given x is equal to x. So what it's basically saying, if I have this input data, what is the probability that it is this class of object, right? So it's basically going, assuming that my input x is this specific x, what is the probability of y? What is the probability of the output? Which kind of thing do I think it is likely to be? Whereas the generator, what the generator is learning the joint distribution, right? Like it's basically saying, I'm learning the joint probability of x and y, which is probability of x given y times p of y, which is equal to the probability of y given x times probability of x. So it's basically learning both bits of information. So it's saying, oh, how can I convert from the output to the input, and how can I convert from the input to the output? Because it needs to know the both directions, which is a little bit strange, right? It makes its job a lot harder, right? And so in order to do this, what we need to do is come up with a really good way of training these models, right? So we've got both of these models and they're going to be acting at the same time, right? And we freeze one and then unfreeze one and freeze one and unfreeze one. But what is our learning? So our learning works like this, right? It's a min-max function. So for those of you who've done AI and done min-max search, think of it a little bit like tic-tac-toe. One of these systems is trying to make the number big. One of them is trying to make the number small. And what we can see here is that we've basically got two components, right? One involves the real data and one involves fake data, right? And the generator generates from fake data some kind of value. And we add these two together. So let's have a look at these two parts, right? So the discriminator attempts to discriminate between the real data X, okay, that's fine, and the fake data G of Z, right? So assuming that theta of G, now theta is weights, is fixed, it attempts to maximize the above function d of X to 1 and d of G of Z to 0. So basically what it's trying to do is it's trying to say, I want this here, which is like me discriminating the real images to be 1, right? But I've also got this 1 minus here, right? So I'm going to run into a problem if the discrimination of the fakely generated data is big, then this number is going to cause me problems and my value is going to go down. Likewise, the generator is doing the opposite, right? So it's trying to generate data which inhibits the discriminator from achieving its goal. So the generator, it is always trying to make this number as big as possible, right? It's trying to minimize this by maximizing the green. Whereas the discriminator is trying to maximize the red and minimize the green. The green is kind of trying to maximize the green and minimize the red, which interestingly minimizes the whole expression, right? And likewise for the max operator, it's maximizing the whole expression because these two things are sort of it's like a zero-sum game. These two things are fighting against each other. Okay, we can see here that like, obviously it's not always great. Like this is another photo and it didn't take me long to get this one from this person does not exist. I would say that the person's face looks relatively like a real person, but what is with this stuff? I don't know. That looks like weird arms or something like, and I don't know what this white light section is. So you can see this is an example where it's really stuffed up. And this is like authentic. Like it's a picture I found rather than one I just got off, like looked for a broken picture. I was just playing around with it and I got a broken picture. I was like, hey, I'll include that in lecture. Just give you an idea of, you know, like, does your discriminator think that this is a real image or not? And if it doesn't, how's it working that out? Is it from these background features and these weird arms? Because it's like, that looks like a face to me. Generative adversarial networks have a bunch of different applications, but one that I thought was kind of cute was image sharpening. So like the idea here, and this is kind of a little bit nuanced, right? So we have an original image, right? And then we can sharpen the image, yeah? But the problem is when you sharpen an image, you introduce artifacts into the image that make it obvious that it's been sharpened. And what these guys were doing, were using generative adversarial networks to basically generate images that look like they've been sharpened, but mathematically are indistinguishable from real images. So they aren't artifactually sharpened. So it's basically, can I doctor an image without you noticing? And the answer is yes. Yes, you can. You can change an image using a neural network to increase its apparent sharpness without it being obvious that it's been sharpened, which is kind of cool. It's also used for super resolution. So the idea here is that like you can infer pixel information from structure, right? So bicubic interpolation is sort of what would happen if you just like zoomed it in. Oh, I just smashed my knee. But you can see here that like using different algorithms, and this is the one that they produced, you can sort of reproduce what the image actually looks like. So you can sort of infer some of the structure underlying this image, right? And basically invent information, right? Because it's been trained on buildings so much, when it sees something that looks kind of like a blurry building, it can make a, you know, educated guess of what an unblurry building would look like, right? So that's kind of cool. All right, now we are onto recurrent neural networks. It's time to, how would I put it? We need to think very carefully because this is complicated. All right, so What are we trying to do? We're trying to say that the input of our model is no longer going to just be its input. What we want to say is it's going to be the input plus some kind of input from the previous go, right? So the idea with a recurrent neural network is that, and the simplest example is video, right? So normally what would happen is when you're processing video, you would give an image and then you would be like, hey, where's the stuff? There is the stuff. What is it a picture of? It's a picture of a dog. Hooray. And then you get to the next frame, you say, that's also a picture of a dog. And that's also a picture of a dog. What a recurrent neural network does is it says, hang on a second, this stuff is like correlated in time, right? So if I had a picture of a dog last frame and it's a video, there's a good chance it's still a dog, right? So I would like to know what it was last time. I want some information from the previous frame. And this can be like the output of a network or an output of a, what do you call it, like a fully connected layer or whatever. It doesn't really matter. What a recurrent neural network is really doing at its core is basically saying, I would like some of the interim information from the previous model, the previous frame, to be incorporated into the new frame. I want to use history, right? So what we end up with is we end up with a structure like this, right? And what we're going to do is we're going to take information from the model so that at t equals 1, we're going to take some of the outputs of the model at t equals 0 to feed into our model at t equals 1. And in order to train it, what we'll do is we'll like have the same structure. The output will generate a loss, and our new loss, our total loss that we backpropagate through the whole model, is going to end up equal the sum of all the losses. And we might have some special weighting to say some losses are more important than others. But the important thing to understand with RNNs, and one of the weaknesses, is if you can imagine that when you're doing your backpropagation, what's happening is it's going to follow this like yellow line from this loss through this output, through this model, back through that model, back through that model, and back through that model, right? So you end up with this situation where, like, if there's any gradient, like if there's any value here that's not 1, the gradient is either going to be like skyrocketing, because every time you go back, you're going to be multiplying by numbers. So you're like, oh, multiply 2 times the error back. Oh, multiply 2 times the error back, 2 times the error back. So every frame you go back, you're going to be exponentially increasing your error. Or it's just your gradient's going to disappear to nothing because you're going to divide by 2 each time. And it'll be like, by the time you get to the 4th one, there's almost no signal left. So that's a basic idea of an RNN, right? And the solution to this is this idea of a long-term, short-term memory unit. So what is the idea of the long-term, short-term memory unit? Okay, we're trying to get rid of the exploding, vanishing gradient issue, right? So we're trying to basically say, we can't have a situation where each of these arrows has the same weight, because otherwise it's going to break. And the way it does it is by incorporating 3 gates to feed information into short-term and long-term memory. And you're like, what does that mean? All right, this is my simplified version of the schematic of what's going on. So if you can imagine that you've got like an old long-term memory and an old short-term memory, and what we're going to do is we're going to pass some of the old long-term memory, and then we're going to pass it through a forget gate. So we're going to either remember or forget some of our old long-term memory. Okay, so far so good. And then we've got a short-term memory, and we're going to add some of our short-term memory to this partially forgotten long-term memory. So we have this old number that we can get rid of if we don't want it. We've got this short-term memory that we can update into our long-term memory, right? And then from this, we can use this to update our new short-term memory, and we can update our new long-term memory. And we have another gate that determines how much of it is maintained into the new short-term memory from our long-term memory, right? And just to explain basically how this all fits together, the input and the old short-term memory are going to be the things that define how these gates work, right? So we have this idea of a forget gate, an input gate, and an output gate. So let's go through them in detail, because I always find like this I sort of get, right? But like I had to sit down and think about this a lot. Okay, so what we're going to do is we're going to take the current input and the old short-term memory. So we have this old short-term memory, right? We're passing these memories, like we have a long-term memory and a short-term memory. We're passing these between each frame of our, let's say, video. Yeah. So from the old short-term memory and the current input, we're going to do some kind of calculation to determine the value of this forget gate, right? Between 0 and 1. And the goal of this forget gate is basically to go, say I had a value of 10 here. I want to forget half of it, so my value will be 5 at the end, right? And I need some way of calculating how much of it I want to get rid of, right? Well, the way that it works here is we take the old short-term memory and the current input, and then we apply a weight to both of them. We add them together and we add a bias, and then we feed it through a sigmoid function. And the sigmoid function, which goes from 0 to 1, will produce the 0 to 1 I need for my forget gate. So basically, if I take all of this stuff in, I can arbitrarily get rid of some of my old long-term memory, which is good because then I can put in some new long-term memory. How much of it do I not want? All right, what's the next bit? Now I have the input gate, right? So the forget gate is basically going, how much of my old long-term memory do I want to get rid of? What my input gate is doing is going, how much of my old short-term memory do I want to convert into long-term memory, right? So this has been gone through the forget gate. Some of it might be there. It might all be there. Now what I'm going to do is, depending on the value of the old term memory and the current input, I'm going to update the value of this input gate. And then some of this information is going to go through and get added to my long-term memory. So how's that going to work? Okay. So basically, we've got two parts here. There's a left branch and a right branch, but these are all part of the input gate. The left branch here, right, takes the old term and the old short-term memory and the current input, adds a couple of weights and a bias, adds it all together and passes it through a sigmoid. That will give me a number between 0 and 1. I'm going to multiply this number between 0 and 1 by something else. So you might be like, oh, okay, that seems strange. So basically what this left component is doing is determining how much of my old short-term memory do I want to pass to my long-term memory. What the right side is doing is determining that short-term memory, right? So what it does is it takes the current input and the old short-term memory, and then it puts it through a tanh function. And a tanh goes from 1 to -1. So what this will allow is it will allow, if we assume that like this was 100%, let's assume that the one on the left is 100%. If it's saying, I want all of this memory to go through, basically, I can send through some value between 1 and -1 to add to my long-term memory, right? So basically, I'm saying to add to this, I can add plus or -1 to my old long-term memory, which to me seems like a weakness because it's like, why can't I add 58 to it? I can't. I can only add 1 or -1. So it means that the scale of the whole system has to sort of operate in this 1 to -1 kind of range, or at least the deltas, like the derivative, like how much it changes from frame to frame, 1 to -1. But yeah, so I multiply them together. So I'm going to get a number between 1 and -1, which is what I want to add. And then I'm going to add a certain fraction of that using the sigmoid to my long-term memory. So I've just added via this input gate some information to my long-term memory. So I forgot some stuff, and now I'm adding some new stuff. Now, the last part is what's called the output gate. And the idea here is, again, I'm going to use my old term and short-term memory to like govern this output gate, right? But basically, the idea here is what we're doing is we've gone through our old term memory to the forget gate. We've got new information coming through the input gate. This information all just goes straight to long-term memory, but I need to determine what my new short-term memory is. And so I have to go through some kind of gating process to determine how much of my new long-term memory is going to be in my short-term memory. And the answer to that is depends on this, right? So again, we have this similar structure. It's exactly the same as the stuff on the left here. We're taking the old short-term memory and the current input, and we are applying some weights and a bias and feeding it through a sigmoid function. And so that will give me another number between 0 and 1. And I'm going to multiply that by my tanh, right? So my tanh is my long-term memory, right? And if you think about it, like multiplying that by tanh basically means that this is going to be a number between 1 and -1. And then my short-term memory is going to be some kind of multiple of the two. So we're going to end up with something between 1 and -1 for my new short-term memory. Okay, cool. So if we go back to our original diagram, this should start making a bit more sense. So basically the idea is we have some old long-term memory and some short-term memory. We're going to determine a new long-term memory and a new short-term memory. The long-term memory, we're going to forget some of it. We're going to add in some extra stuff to it, and then we're going to store it. And for the short-term memory, what we're going to do is we're going to take some of the long-term memory, we're going to gate it through an output gate, and then we're going to store that in the new short-term memory. And just as a reminder, all of these gates are determined by all old short-term memory and the current input. And that's how it basically works, right? Oh, that's not in the right place. Let me just fix that. RNN applications should go, where should it go? Here we go. Should go after RNN issues, right? So RNNs are used for all kinds of things like audio data, text processing, anything that happens in time, right? So like text is a good example because each word is considered a different epoch in time, right? So I want to convert some, a sentence to another sentence, maybe translate a language from one language to another. I get each word in turn, or maybe I want to do text prediction. I get each word in turn. I want to predict the next one. And that's what ChatGPT does. ChatGPT just each word, it's trying to predict what the next word is. It seems like a very complicated RNN application. It uses slightly different technology. There's also gated recurrent units. I'm not going to go through them in detail. It gives you basically it's the same thing but slightly different. So an RNN basically just has a 10H function. The LSTM has this complicated thing with the forget gate, the input gate, and the output gate, which you can see here is FT, IT, and OT. The GRU, which my PhD student used for like some stuff, basically it's got an update gate and it's got a reset gate, and the update gate can be sort of like, I don't know, it's it's sort of like the output gate a bit, like it's the stuff that puts the data into the new state, and then the reset gate is the data that comes out of that state. So we're going to store like a special state, and you can see here it's going to store something, right, that goes across with each time frame, but it's not nearly as complicated as this one, which has got several things coming in and out. And they have similar performance. There isn't a lot between them. GRUs, I think, are slightly more efficient because they've got slightly less components. And I think that's it. That's everything that I've got to discuss on deep learning, I think, or at least the summary of it. If I were to offer a summary, don't use it too much without knowing what it does. It takes a lot of experience to get used to deep learning. You need to get a sense of how big your data sets are, how much data you have, padding your data, augmenting your data with extra things, designing a sensible structure that solves the kind of problem that you want. Are you doing like audio processing? You should probably be using some kind of LSTM or some variation on an RNN. Are you doing image processing? You should be using a CNN of some kind. There are also one-dimensional CNNs and three-dimensional CNNs for video data. There's a lot, there's a big field. But if you just want a very simple classifier, if you have a very big data set, sometimes you can just take the big data set, run it through a deep neural network with lots and lots of layers, get the output that you want. And if you have enough data, you should be able to train it. And what you're really hoping for is that the amount of data that you have is really big. The problem that we have is that the amount of data that you have is often smaller than the number of parameters, in which case overfitting is very common. But there are lots of strategies that you can employ to reduce the amount of overfitting. But this covers off the main, the main kinds of, where are we? If we go all the way back to the beginning, it covers off the main kinds of neural networks that are state of the art. And you'll find that a lot of state-of-the-art neural networks are basically this kind of structure. One of these, they're a CNN or an autoencoder or using GRUs or LSTMs or each of these things. All right. Other than that, I hope you all have a really good holiday. Okay, bye.